Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. It's my pleasure to welcome Hongji Wang to give us a talk this afternoon. Hongji just defended his PhD thesis at the Stevens Institute of Technology, which is just across the Hudson River from Manhattan. And he's been doing a lot of work with his advisor, John Oliensis, on perceptual organization. He's going to tell us about some very interesting ways to do segmentations, in particular to deal with the uncertainty associated with segmentations.
All right. Thank you. Thank you for attending this talk. And in this talk, I will try to describe the major work I did in my thesis work, which is trying to use image segmentations to do shape matching. As I will show you, this work can be applied for image segmentation and for shape matching for both tasks. And I will describe the applications for both areas. So first, I will give you some brief context information for this work. The recognition problem is a very interesting topic. Given the images, we want to know what object and what scene, what activity is going on inside the image. But recognition is a very tough problem. Just like the example I showed here, even though these two images have very similar content, have similar object inside the image, but the appearance of the two images can be quite different. And many factors can contribute to this appearance variations. For example, the viewpoint of the object, the skew, the illumination, and the deformations. All these factors make recognition a very challenging problem. And when we talk about the recognition, there are some fundamental issues related to recognition. And the first one is the representation issue. It's also called it is also the so-called local versus global dilemma. Globally, the whole image contains rich information which is sufficient for recognition, but it is very hard to work with because the huge appearance variation. And in another word, it means it is very hard for us to find a correct matching in a global image level. On the other hand, if we can use a local image patch, it will be much easier to work with because the appearance variation is much smaller, but it may not contain sufficient information for the recognition task. So that's the issues. Another important issue is the features we can use for recognition. So far, the most popular features are using the textures and edges. And recently, the image segmentations has also been applied for object recognition. So next, I will give you some more discussion about these things. Actually, I'm sure you're already familiar with this, but I just, okay. So since the global image is not very easy to work with, so currently the most approach is using local features. So we have to find some way to clarify the local ambiguity somehow. The bags of features technique attempts to use as many features as possible. And the good thing about it is it can be learned very efficiently using the support vector machine technique. Another type of approach also considers the spatial relations between the local features. This way, it is more efficient to clarify the local ambiguity, but learning becomes harder because to find the optimal solution, we have to search over a combinatorial space, right? And recently, there are some techniques try to combine these two, for example, the fragments approach. Compared to the texture features, the edges usually are more robust to appearance changes caused by illumination change or viewpoint change. And more importantly, just like shown in this example, edges tells you the shape of the object, which is a very distinctive feature for recognition. So next, let's take a close look at the shape matching problem. Again, when we try to compare the shapes, we are facing the global and the local dilemmas. The global shape is very distinctive, but it's very hard to work with because of the huge possible deformations, right? And on the other hand, the local edge fragments is easier to work with, but is not informative enough. So currently, for reliable shape matching, usually we need to find the point-to-point edge correspondence, which is very expensive because it requires to search over a combinatorial space.
But not only that, you have to account for scale and perspective.
Yes, ideally you should account for the scales, but in this talk we assume the shapes you are trying to match already have a similar scale and already have a similar orientation, something like this. Just like the example showed here. It's a simplified task of shape matching. Yeah. And recently there are some techniques try to combine the advantages of global and the local shape matching approaches. For example, this one, instead of using just the edge fragments over here, they try to group the edge fragments first. So after grouping, the shapes becomes more distinctive, but it is still simple enough for us to work with. So it's kind of like an intermediate solution between the global and local approaches. The limitation for this method is that boundary grouping is not reliable, so they have to use based on using training images and based on learning techniques. So it is not very good to compare arbitrary shapes when you don't have training data for the problem. Another interesting technique using histograms of edges or histogram orientation of edges to represent the shape. And this method is very simple. It doesn't require a point-to-point edge correspondence, and it is robust enough to overcome small deformations. It is one of the most successful techniques available so far. The major limitation is that histograms is an information loss compression technique. So basically, it will sacrifice some shape description accuracy. Just like the example showed here, if you just count the histogram over the region over here, these two shapes actually have the same histogram, but actually they are different shapes. So after a brief review of the techniques, here comes close to the work I did. For the shape matching problem, our work is based on the intuition showed over here. When we try to compare the two shapes, we can transfer the edge consistency into region consistency. By region consistency, I mean how well the two regions overlap to each other, just like the example showed here. This way, you can detect any small shape difference, and it is still you don't require the edge correspondence between the two shapes. And since the regions are global features, and they span over large regions, so it is robust to small shape variations. So these are the advantages using this strategy to do shape matching, which is listed over here. But when we try to using regions for shape matching, it also has some issues we have to take care of. The major issues is since regions are global features, so it is very hard to represent and compare precisely. And more importantly, regions usually it is very hard to retrieve good regions from images directly. So all these issues we need to take care of. And in my work, I try to address these issues to make this idea more practical and more efficient. So here is a brief overview of the solutions for each issue. So for representation problem, we propose to use image segmentation to represent the shape and to compare the shape. And for matching, we use mutual information to do the comparison. To address the unreliability of segmentations, we give a solution to average over all the possible segmentations. So next I will give you the detail for each part. The first part is using image segmentations. The first thing I want to mention is image segmentation has been used for recognition before, but mostly the image segmentation has been used to represent appearance. In this work, the major novelty is we propose to use the entire shape encoded in the segmentation to represent the shape. And as I will show you, it allows very efficient shape matching algorithms. Just like the example I showed here, good segmentations usually contain sufficient boundaries for shape matching. And also using segmentations to represent the shape has some other advantages. The major one is image segmentation algorithms usually using the global image information to compute the boundaries. So they have better chance to find the true boundaries than local edge detectors. Another major advantage is, as shown in the images, the image segmentation reveals the global shape structures of the image, which is more distinctive than local shapes. But the limitation of segmentation is it can be unreliable. Just like the example showed here, sometimes image segmentation does not have sufficient boundaries for us to do the shape matching. But over segmentation can be partially address this problem because it can has a better chance to locate the true boundaries. But the point here is over segmentation is not sufficient because they add too many fake boundaries inside the image. So it makes the overall shape description less accurate. So we will come back to this issue later. Actually, this is the major point. To addressing this problem is the major novelty in this work. The next point is when we have the shape of the segmentation, how can we compare them? The intuition we used to compare the shape of segmentations is shown in this image. So if suppose we want to compare the segmentation with the two segmentation in the middle, the red column shows the joint segmentation for these two matching problems. The joint segmentation is simply just to overlay the boundaries of coming from these two segmentation. You have the joint segmentation, right? The intuition here is if the two segmentation have similar shapes, in their joint segmentation, their boundaries tend to overlap to each other. So this will give you some large segment, in the joint segmentation, just like the body of the car. On the other hand, if they don't have similar shapes, in their joint segmentation, the boundaries don't overlap to each other. So this will give you many small segments. So that's the intuition we use. And the good thing about this matching strategy is that this intuition actually is well captured by the mutual information concept. So the idea here is that we want to use mutual information to measure the similarity between two shapes. All right. So before we go ahead to show how to measure the mutual information between images, between segmentations, we first need to know how to compute entropy for segmentation. For this purpose, suppose you have a segmentation like this. If you just randomly pick one pixel out from this segmentation, the p sub I represents the probability that this pixel is coming from the nth segment, right? So p sub I is actually equal to the area proportion to the whole image, just like shown in this image. For this one, we have 6 segments, right? And so basically, the p sub I represents the probability distribution represented by the segment size for this segmentation. Then, using the standard entropy definition, we can compute the entropy for this segmentation, right? And we call this structure entropy because it actually gives the a structure complexity of the segmentation. Just like shown in this example, these are 2 segmentations for one image, but the left image has fewer segments and has fewer boundaries. So measured by the structure entropy, it is much smaller than the other one, right? Okay, so actually, after knowing how to compute the entropy for segmentation, it is very straightforward to use the standard mutual information definition to compare the similarity between 2 segmentations. So here is one example to using the mutual information. Suppose A and B are the 2 segmentations we want to compare with. This segmentation shows their joint segmentation. And below, it shows the structure entropy for each segmentation above. Right? For this case, A and B, they don't really they contains orthogonal information, so they don't tell anything about each other. So the mutual information between them is 0, which means they are totally different, right? By the way, is there any questions so far? Okay. Also, in the context of recognition, it's usually very useful for us to normalize the mutual information. In our case, we normalize the mutual information by the joint entropy. So after the normalization, the metric is between 0 and 1. With 0 means they're totally different, and 1 means identical shapes, right? So here is another example to using this metric to compare the shapes. These two segmentations are labeled by different human subjects for the image over here. And this one shows their joint segmentation. And as you can see, it's pretty consistent for these two, but there are still some minor difference in this section and this section. And using our metric, we can successfully capture this fact. All right. All right. At this point, I will take a few minutes to give more discussion about this segmentation-based mutual information metric. Because as we know, the mutual information on intensity image has been available for a very long time, mostly for image registration applications. So here we are trying to use mutual information on image segmentations. So what is the major difference between these two techniques? The major difference between segmentation and intensity image is that for image segmentation, if two pixels are coming from one segment, they have to be spatially connected by the pixels coming from the same segment. But for intensity image, there is no such constraint. And so this is a spatial constraint difference between these two. And because of this difference, using image segmentations, the matching results is more robust to small shape variations. But using intensity images is more sensitive to such changes. So here is an experiment I did to show this property. For this test, what I did is I tried to compare the similarity between a segmentation with the shifted version of the same segmentation. So as I shifted the segmentation away, I want to see how the similarity changes. And the x-axis actually gives the shifted pixels between the two images. And the y shows the normalized similarity between the two images, right? And for this one, I used structured mutual information on segmentations and mutual information on intensity images, right? As we can see, using intensity image is very sensitive to the spatial shift. With the first pixel moved, it drops very largely. But using segmentations, we have pretty good robustness against this test. So basically, this means intensity mutual information is better for registration, because for registration we expect the two shapes to have very close matches. But for recognition, it's a different story. For recognition, it's very rare for us to find the two identical shapes. So we want the matching technique to be more robust to this kind of variations. All right. So the last part is how to address the unreliability of segmentations. All right. Since any specific segmentation can be very unreliable, so our idea here is we don't want to base our decisions just based on any specific segmentation. Instead, we want to use all the segmentations, but weighted by their probabilities. And so basically, this is the idea. So here is shows how to use this idea. Okay, recall, given a segmentation, the structure entropy for the segmentation is defined over here. But now, given an image, since we want to use all the segmentations for this image, so we define the average structure entropy for this image, which is defined over here. The capital S is one candidate segmentation, and the P gives the probability of this segmentation for this image. And the SEG represents the site of containing all the possible segmentations. So basically, this is a very straightforward definition. It's trying to using all the segmentations, but weighted by their probabilities. Right? So to show how to use this definition, here is a toy example. For this simple example, I just consider an image only have 4 pixels. So for this case, we can enumerate all the possible segmentations over here. There are 15 possible segmentations for this image. For example, this one, if 2 pixels are in one segment, there is an edge between them. So for this one, we have 4 segments, right? For this one, we have 3. For this one, we have 2. To compute the structure entropy, we need to know the probability for each segmentation. For this case, if we assume each segmentation has the same probability, then we can have the average structure entropy for this example. So here is the procedure how to compute it. Since each segmentation has the same probability, so the P here is a constant. It's 1/15. So all we need to know is the structure entropy for each segmentation over here. And here is one example to compute. Here's another example. But unfortunately, this definition is not very useful for us to compute average structure entropy for real images. Because first, it is very hard to compute the probability for each segmentation. And second, it's impossible for us to enumerate all the possible segmentations for real images because there are too many of them. So the major part is we try to give a solution how to efficiently approximate this computation over here. For approximation, our work is based on the observation over here. When we try to compute the structure entropy, we can consider the contribution from each pixel separately. So here is what I mean. Recall the structure entropy is defined over here. It is based on the size, the number of segments. N sub s is the size, number of segments over here. The observation over here means we can rewrite this definition into another form. In this form, it is actually considers the contribution from each pixel separately, which is the sum over it. And the contribution from one pixel is defined over here. And the n is the image size, and s superscript m is the segment containing this pixel m. A gives the area of the segment. So the whole thing inside the log actually corresponding to a p sub I over here. Yeah.
So why don't you use the standard deviation of the brightness distribution within a segment?
Within the segment for
Let's say if you have a segment and all the pixels there have a high standard deviation, then you would have a different weight, right?
yeah.
So, but you're not doing that.
You mean using the distribution of the intensity for
The segment to be a measure.
measure of
How
what?
reliable the segmentation is.
Oh, it is a possible way to do that, but I think this way is more straightforward because it's just based on the probability of the segmentation directly. And using the standard deviation is just one way to evaluate the probability for the segmentations, right? And but the work here is we don't really take care about too much how you evaluate the probability for each segmentation. But once you have this evaluation, here is a way to show how you can combine all these evaluations to get one more reliable results. So it's a kind of different concerns, right? Yeah. Okay. So, okay. So, which means when we try to compute the structure entropy for segmentation, all we need to know is the size of the segment containing each pixel. So this observation actually is not very useful to compute the structure entropy for a single segmentation, but it is very useful to compute the average structure entropy for an image. Okay, so now we can transfer the observation to a average structure entropy. Again, here we can consider the contribution from each pixel separately, and the contribution from one pixel to the average structure entropy is given in here. It is actually average over the contribution from this pixel to all the segmentations, but weighted by the probability of the segmentation over here. Recall the contribution from this pixel to one segmentation is defined over here. If we put the probability term inside the log, what we have is something, pretty nasty, but it has a very simple meaning. The meaning is it gives the geometric mean segment size containing this pixel across all the possible segmentations. All right. So here is a summary for the observation we are using for approximation. So to compute the structure entropy, all we need to know is the size of a segment containing each pixel. And similarly, to compute the average structure entropy, all we need to know is the geometric mean segment size containing each pixel across all the possible segmentations. Right. The geometric mean size is pretty hard to compute, but we are more familiar with the arithmetic mean, which is also easier to compute with. So our idea here is we want to use the arithmetic mean to approximate the geometric mean. So here comes the approximation part. All right. Fortunately, there is a standard approximation for this purpose. Here is the geometric mean. This is the arithmetic mean, and here is the variance of the segment size of segment containing each pixel. So basically, this approximation is derived from the Taylor series by ignoring all the higher order terms. So we are only using the first two terms for this approximation. All right.
So when do the higher order terms become insignificant? Is when the number of segments is large, or what?
I'm sorry.
So you say that it's a Taylor expansion, and you say that the high order terms drop off. But I'm just wondering, when do they actually drop off? Is it when the number of segments become large, or what?
For this part, I don't really know actually. I didn't study this part. But the thing is, in my experiment, I test, I evaluate the significance of the second term compared to the first term. Actually, this term is already, contribution is much smaller compared to the first term. It gives you some insights, for the higher order terms, the contribution will be much smaller, usually.
Okay, I'm curious what makes the higher order terms drop off so quickly. I mean, that's all right.
Yeah. Another way to think about it is to consider the variation of the segment size compared to the size of the segmentations. Basically, the variation term, this term is not very large. So this means the variation, divided by the size of the segmentation, is not very huge. But the variation term is, it is related to the, as I will show you, when you compute the arithmetic mean and the variance, it is based on the image affinities between pixels. So if the two pixels have a very high affinity close to 1 or very low affinity close to 0, usually this term is very small. But if the affinity is not very certain, say around half, something like that, 0.5, this term becomes larger. So it's related to how confident the segmentations is. It's maybe later it can become clear. All right, to compute the arithmetic mean, what we can do is we use the affinity matrix. The affinity between two pixels actually can be interpreted as the probability that these two pixels belong to one segment. So when we try to compute the arithmetic mean segment size for one pixel, what we can do is we just sum over the affinities between this pixel and all the other pixels. So that's the arithmetic mean segment size. So how can we compute the affinities? Actually, to compute the affinities in the practice is not very hard. For example, we can use a Gaussian function based on the intensity values to evaluate the affinities between two pixels. So if two pixels are very close to each other and they have similar intensity values, so they should have a high intensity, high affinities. Otherwise, they should have small affinities. The next question is how to compute the variance. To compute the variance is a little bit difficult. So we make an assumption. We assume the pairwise affinities are independent from each other. This way, we can ignore all the covariance between the affinities. So the variance can be simply computed over here.
So when you work with these affinities, do they have to be normalized properly to be an actual probability density function?
Yes, at least it should have a probability meaning. Mm-hmm. So it should be between 0 and 1, with 1 means they are definitely in one segment. 0 means, something like that. But the independent assumption is even though the independent assumption is pretty common in image segmentation community. For example, the normalized cut is actually compute a maximum posterior solution based on this assumption. But this is still a very strong assumption. So our concern here is how much accuracy we actually lose when we use this assumption. So to investigate this problem, I did the following experiment. in this experiment, I use real images from the Berkeley's testing benchmark segmentation database. So given you real images, for each pixel, you can evaluate the geometric mean using and without using the independent assumption. So we want to compare how different these two approximations are. For this purpose, we are using the ratio between these two approximations, right? So if the ratio is close to 1, which means the independent assumption doesn't really give you too much difference, so we can safely use it. For this one, it shows the empirical distribution of this ratio over all the test images from the Berkeley's segmentation data set. As you can see, for most of the cases, over 90%, this ratio is very close to 1, which is larger than 0.8. Okay, which means, in practice, the independent assumption doesn't really give you too much difference, for the approximations. So we can very safely to use this assumption to do the approximations. All right, so here is coming back to the toy example we saw before, which we know the ground truth value is given over here. If we're using our approximation without the independent assumption, the approximation is very close to the real one, right? Using with the independent assumption, the error is larger, but it's still pretty close to the real one. All right, so now it's time to show how to compare this. Yeah.
Is the difference an underestimation typically or an overestimation typically? It's usually an underestimation.
For the first term, it's over a little bit, but for the second one, if you ignore the second term, it's a little bit under. Yeah. For this example. Yeah. Okay. So to show how to compare the similarity between two shapes, between two images based on the shape, here is the equations. So given two images, again here we want to compare the mutual information between their segmentations over here. But to address the unreliability of segmentations, we're averaging over segmentations for both images over here. So this is the definition. Again, the definition is not very useful, but the good thing is we can rewrite it into another form. In this new form, the first two terms are the averaged structure entropy for the two images, which we already know how to approximate it. The last term is the average joint structure entropy for the two images, which actually can be approximated using the same way, but using a different affinity matrix. The joint affinity matrix is just simply, you multiply the affinities coming from these two images. That's it. Okay, so here is the final approximation to compare the shape similarity between two images. In the numerator, it is corresponding to the average segment size in the joint image. In the denominator, in the denominator, it's corresponding to the average segment size for the two images separately. So overall, it measures the statistical independent level between the two images.
Let me see if I'm still following this. So M1 of Mn, you take 2 pixels in image 1, and you compare their gray levels. And if the gray levels are close, you say it's close to 1. If the gray levels are far away, you say it's close to 0, right? You pass it through a Gaussian. You can do that for image 2. You can pick up the same pair of images, pixels, but it's a different image, so the colors will be different, right?
Yeah.
And now for the top, you're saying we just basically multiply those two numbers, right?
Yes.
Okay.
And basically, this is just one way to compute the affinities using the Gaussian and the intensities. Okay. There are some other ways. And also, when we're using the Gaussian and the intensities, we enforce a spatial constraint. So if the 2 pixels are close to each other, we use this Gaussian to compute the affinity. Otherwise, we just consider the affinity to be 0 or something. Ignore it.
So basically, if the pixels are very similar in both images, then
which means
this
in the joint image, they also have a high probability to be Okay,
but if one image is similar and the other image is different, then something's different, and that's more likely to be low.
Yeah.
So, Okay.
So basically, it encourages the two affinities to have a similar, response.
Yeah.
Yeah.
Okay.
All right. So here is a summary for this part. Since averaging over segmentations is derived from segmentation matching, so it gives it has all the good properties using segmentation for shape matching, but we don't suffer from bad segmentations too much anymore. And even better, we don't have to need to compute actual segmentation for shape matching at this point.
No. When you say compute segmentations, do you mean normalized cuts, or if you were to compute segmentations, what class of algorithms would you be running?
Anyone you can use normalized cuts, mean shift.
So mean shift is also defined in terms of affinity matrices?
In a way it is. In a way it is, because it's based on the kernel stuff. It doesn't really have to. It doesn't really require the segmentation to have the segmentation algorithm to have the same interpretation as we formulated. When you try to use the image segmentation to represent the shape and to compare the shape, whatever the segmentation algorithm is, we only care about the segmentation itself.
But you're making the assumption that the affinities capture the important information in the image, right? The only thing you ever look at is the infinities. So you must be implicitly comparing yourself against algorithms that segment based on those affinities.
Yes,
if you pull a totally different segmentation algorithm out of the hat, your approximation wouldn't be interesting. Right?
Yeah, that makes sense. Yeah, you're right. Yeah.
So I'm sort of curious, what is the range of segmentation algorithms that exploit the kinds of...
But actually, as far as I know, most available, at least the most leading segmentation algorithms are based on this, assumptions, based on the affinities of pixels to do the groupings. So that's...
what are some of those algorithms?
For example, the mean shift, normalized cut, and also there are some graph theory-based segmentation algorithms. Actually, implicitly or explicitly are also using the affinities between the pixels, actually. Yeah. Right. And so next, we can show some applications using these approaches. First, we show how to use the algorithm for perceptual organizations, for image segmentation, and for image smoothing. For the application in image segmentation, our motivation is that low-level image segmentation is a very ambiguous process. Just like shown in this example, these are the the ground truth segmentations labeled by human subjects, right, for one image. As you can see, there are big variations across the different segmentations. So the huge variations shows that the plausible image segmentation usually have a flat distribution. So for random variables with a flat distribution, the mean estimator statistically should be more robust than the maximum posterior estimator. The point is that our approximation technique allows us to compute the mean estimator for to compute the image segmentations. All right. So let's first recall the definition of mean for random variable, which should give the least variance for this random variable with respect to some distance metric. Formally, it is defined over here, and this represents a distance metric for this random variable. Okay, so in our case, we can compute we define the central segmentation, which gives the least average distance to all the other segmentations. So formally, it is defined over here. Here, the capital V represents a distance metric for image segmentations. It is the variation of information. Basically, it is a variance of mutual information. Actually, it's equivalent to mutual information. Minimize this distance is equivalent to maximize the mutual information between the two segmentations. As you may already see that actually this is not an exact mean estimator because we are computing here using a distance instead of distance squared. But it's kind of trivial, but we can show you that the central segmentation is the mean estimator with respect to the distance metric of square root of v, right? The major point is our approximation approach allows us to compute this function, this cost function. So we can minimize this cost function to search for the optimum segmentations. So here is one way to search for the optimal segmentation. We can use here we're using gradient merging. Where are the labels? All right. So basically, initially the segmentation is a trivial one. So each pixel is an individual segmentation. So we keep merging the neighbor segments as long as this merging can decrease the cost function, and we stop merging until we cannot decrease the cost function anymore. All right. So this is just one way to do the optimization based on the approximation. But for general image segmentation, we can use a gradient descent optimization procedure. So here are the demos to show the process. So at each round of the optimization, we are just using the derivative with respect to the cost function to optimize to update the segmentations, and until we converge to a local minimum. Right. Okay. So for quantitative evaluation of the segmentation results, we propose a new criterion to compare to evaluate the quality of the segmentation, which is the average distance from this segmentation to the ground truth segmentations. Right. Here is an example to show how to use this criterion. And all these segmentations are labeled by humans, so they're considered as a ground truth segmentation. And below each segmentation, it shows the average distance from this segmentation to all the other ground truth segmentations. The criterion states that the smaller the average distance is, the better the segmentation is.
Again, here when you're comparing two segmentations, you're using that very early definition.
Yeah. So you don't have to average over all the segmentations, because the segmentation for this case is very definite.
Overlaying the two segmentations, taking the intersection of all the regions and then computing the.
Yeah, exactly.
Okay.
So using this criterion, actually, this segmentation is considered as the best. And it also has a meaning, on average, this segmentation is most similar to all the other ground truth segmentations. Right. So using this criterion, we apply the segmentation algorithm on the Berkeley's test images, and we compare it with a mean shift, normalized cut, the efficient graph, developed by 1,000 swab, and in here for each test images we segment the image into different number of segments. The number of segments we use are 10, 20, 30, 40, and 70, and then here this value gives the mean of average distance for each test images. As you can see, our approach actually is more consistent. Performs more consistently than the competing methods, and overall it performs much better than the competing approaches. Okay, another application of this method is to use it for image smoothing. Since our approach actually, this thing measures the similarity between two images based on the term of their segmentations. So we can ask one question, given image I, what is the most similar image to image I? And formally, it is defined over here, right? So we want to find the image, the optimal image should be the most similar image to the image I. The answer is it is different from the I, actually. And it is a smooth image, but the boundaries of the image is preserved. So here is two demos to show the smoothing process. On the first row is the original image. So we optimize we try to find the optimal image starting from the original image. We try to maximize the similarity between the lower image and the upper image. As we can see, actually this value here shows the mutual information is actually increasing, but it's very small. You can see here. But the point is, as the similarity increases, the image becomes quite smooth with the boundaries, with the major structure is preserved. The reason for this is as as we compute the central segmentation, the central segmentation actually is the most similar segmentation to the whole image. So you can see that for this optimal image, it should have a distribution of segmentations very tightly clustered around the central segmentation. So as you optimize this image, the distribution gradually cluster around the central segmentation. And during this way, the image becomes smooth, and the structure is very close to the central segmentations. Yeah.
So you're saying the smoothed image, when run through a segmentation algorithm, will have a segmentation that is most similar to
the central segmentation we saw before.
The central segmentation for
the original image.
For the original image.
Yeah.
Okay. So you have your algorithm will take an image and over all possible segmentations will compute the one that is most central.
Yeah.
For some range of segmentations, right? For some algorithm that generates segmentations.
No, it's actually you can think like this way, because the algorithm is based on the affinities, right?
Yes.
Basically, after you compute the affinity for an image, it implicitly defines the distribution of the segmentations for this image, and it computes the central segmentation and the smoothing based on those distributions. Yeah. All right. Okay, so the next application is for using it for shape matching. The first one is for object detection. For this case, given the image, we want to see if there is an object inside the image, and where is it. Currently, to address the global appearance variations, most approaches using semi-local features. As I will show you, using our approach, we can using a global template matching, we can still achieve very excellent results. The detection procedure is we first need a template for this class. Then we using a scanning window across the image. Then we use a threshold to detect the image. As I said before, we assume the object has similar pose scales already. The database we use first is the side view database. For this database, the car side view database. For this database, we already have some training exemplars. So we use the average affinity matrix as our exemplar, as our template. To give you a rough idea about the shape structures for the template, here this image shows the rough structure. The intensity for this image is corresponding to the segment size computed from the arithmetic mean segment size for this image computed from the average affinity matrix. So if it is bright, means the pixel is standing in a large segment. If it's dark, means it's close to a boundary or in a small segment. The other two databases we use are the human face and the car rear view database. And all right, so here are some detection results. We first compare our methods with the similarity template approach and the probability index approach. The reason we want to compare with these two is these two methods are actually also comparing the image similarity based on image affinities. The only difference is that our approach is derived from the image segmentation and the mutual information. So we have a better statistical meanings than the competing metric. As we can see, our method also performs much better than the competing approaches. So here we are comparing with two shape matching techniques which are based on local shape features. These two methods are actually using a similar training and detection approach strategy as we did. Given some training images, they first try to figure out which edge fragments is the most informative for this class. Then they try to using the learned classifier to label the object in the new test images. And again, our method also performs better than the local shape matching approach. This shows the importance of using the global shape for shape matching. Right. All right. So the last one application is for shape-based tracking. The reason we want to use shape is more specific than the appearance histogram representations. But currently, most shape tracker are using snakes, which only use the silhouette of the object. And if you want to include the inner shape, if you want to use the complete shape of the object, usually you have to use some training algorithms. But here we show that using our global template matching approach, we can use all the detail shape. Right. For this tracking algorithm, given the first image, you label the object you want to track. It will find the most similar one in the next frame in a small neighborhood. Right. So here shows some tracking videos to show the demos. Again, on this coordinate shows the rough shape structure of the template it's using now, the same way we computed it before. To handle the occlusion, we just average smooth the template across the time. So this way we can handle the occlusion part. Right. And here we try to compare the shape matching algorithm with the pyramid histogram of gradients. This pyramid histogram of gradients is based on the edge detection and is also considered as a global shape matching algorithm. And so the test is here is against in the video sequence with great lighting changes. As we can see, since the pyramid histogram of gradients is based on local edge detection algorithms, it is very sensitive to illumination changes. But our approach is based on averaging over all the possible segmentations, so it is more robust to this type of changes. So it gives us some more. Here is the rough structure of the shape, more accurate tracking results.
So that image in the lower left corner, what is that?
This one is the rough shape structure for the template it's using now.
And the shape structure is again visualized by the gray encoding the size of the region, the average size of the region. It's like we showed us for the car.
Yeah, exactly. All right, so here is the conclusion. The major point of this work is first we propose to use image segmentations to represent and compare the complete shape in the image. And we use mutual information to do that. And to address the unreliability of image segmentations, we give a solution to average over all the possible segmentations. And this approach can be applied for shape matching and it can be applied for image segmentations. And yeah, pretty much that's it. And yeah, that's the work. So any questions?
Well, thank you for your talk.
Thank you.